Okay, exam on Friday. Same rules for all the other exams. You're going to get 1 page front and back for the final. Oh, one thing about the final. Do we have everyone here? Oh no, we're missing one person. But for the final, who is okay having it on the last day of class versus having it in the finals? Because I have it listed in the finals. Who's okay with the last day of class? Everyone can be here. There's no one's going to be missing that. Okay, because I just want to make sure if I'm making a change, especially with the final exam schedule.
What's the last day? What do you mean last day?
Last day would be December 6th, I think. It's a Wednesday. And so if anyone is out, we can try and make an arrangement so you can take a little bit before, a little bit after. But I have to be traveling to London, actually, to do some neutron scattering experiments. And so it'll be difficult for me to be around for the actual final. So if you guys are all okay with having a shorter final, right, only an hour-long one, and we have it during the last day of class, sounds like that's not going to be a huge objection. So let's consider that a done deal, and I can update the syllabus and remind everyone of that as we get closer and closer. Homework questions. Oh, sorry, Randall, let me finish up. Closed book, closed notes, you get 1 page front and back for the final. You can have 2 pages front and back, so you can just kind of staple the 2 ones that you've written up together, or add stat mech to it or something like that. You'll have an equation sheet. Everything you need to solve the exam will be included. There is potentially going to be, obviously, non-linear mathematics that are required. If there's a system of equations, or if there's a non-linear equation you're expected to solve, I'll find creative ways to allow you to do that, either by giving you a list of options. So if you've derived the right equation, you can plug them in, and hopefully one of them spits out a 1 or spits out a 0, or whatever you think is appropriate. Expect lots of charts. Expect charts that you haven't necessarily seen before. But the notion there is that we should be able to take any sort of a phase diagram and dissect what's going on in the process. Right? Remember, phase equilibrium is obtained, for the most part, constant temperature and pressure. Right? So if you're given a temperature, a pressure, and a composition, that should lock you in a spot on a phase diagram. Recall, right, either constant pressure or constant temperature is going to be a horizontal line. Constant composition is going to be a vertical line. So when everything intersects, that's the position that you're at. If you see lines nearby, that means those are probably the lines for your phase equilibrium. If there's no lines, that means you're probably single phase, and so on and so forth. So who's looked at the practice exam? Okay, so there's an example of a phase diagram that you haven't seen before. It's a vapor, I think it's a vapor-liquid-liquid equilibrium mixture. So for that one, no, maybe it's only...
It's like vapor, liquid, solid.
Yeah, that's what it is. Sorry, it's vapor, liquid, solid. In the past, I've done vapor, liquid equilibrium mixtures. But this one, I think, is, liquid, liquid, solid. But you should be able to interpret phase diagrams. So I think Justin would be able to handle a solid phase diagram, so maybe you'll get one of those. I don't know about that. I'll probably try and keep it to more fluids, but yes. Okay, questions?
Will there be practice exam for the final?
No. I'll try and give out some stat mech practice questions, but then the practice exam material will all just be the practice exams for 1 and 2. Homework questions?
2B.
Yep.
During that energy balance, I'm just in trouble understanding where the enthalpy of vaporization comes into play.
It can come into play in many different locations. Let's go over that one. This is a good example. So on this homework, it's going to be a challenge to double check numbers. And so the key thing is you have to make sure you got the procedure right, because the procedure is what I'm going to be replicating a little bit on the exam. So question 2 is we're dealing with a flash calculation. So effectively, you've got a feed, you've got a top and bottom stream. The temperature is fixed at 298. The pressure is what is variable. I don't remember what I said. I think, 4.6 kilopascals. So if I did everything correctly, that should be in the 2-phase region for this mixture. This is the heptane toluene. So the one thing that's a little bit confusing is the paper that I uploaded has toluene as component 1 and heptane as component 2. The reasoning for that is that they held toluene constant, then they varied the second component to look at the vapor-liquid equilibrium and the activity coefficient models. by having toluene is constant and they just cycle through a couple other compounds. But I recommended that you put heptane as your component 1. So if you look at the PXY diagram, it looks kind of a little bit shaky, but it kind of looks something like this, I think. And if you kind of read through the manuscript, they talk about how, based on the shape, we would expect there would potentially be an azeotrope forming if you change the pressure or temperature a little bit of this mixture. So the idea is that you are going to fit this PXY diagram, calculate the excess Gibbs, tune it to an activity coefficient model, take that model, plug it in to do a flash calculation, then additionally use heats of mixing to determine what the energy balance on the process is. Truth be told, the contribution to non-ideal liquid phase mixing is not super major on the overall energy balance, but the procedure I think is critically important to understand. So a lot of double checks built in. So for this mixture, it should be in the 2-phase region if I assign the question correctly, so you can always double check with the PXY diagram to make sure that your flash calculation works out well. So, energy balance on this system. All right, so let's not forget that our humble origins and energy balance is before we talked about phase equilibrium. So, energy balance, first step du dt, what is that equal to?
0.
Why is that?
Steady state.
Yeah, so it's a steady state process. So all we're doing, remember, with energy balances and entropy balances is we're being accountants. We're just keeping track of all the energy in and all of the energy out. So coming into the system, we have a flow rate of the feed. I'm not going to write the summations because this is a simple problem. I don't have to write the general balance out. We have the flow rate of the feed times by the enthalpy of the feed. Leaving the system, we have the flow rate of the liquid times by the enthalpy of the liquid, and leaving we have the flow rate of the vapor times by the enthalpy of the vapor. So the flash calculation part is something that I think everyone should be pretty confident on handling. If you've done it on the past couple of homework assignments. It's the enthalpy now that we have to worry about. So which of these streams, well, I guess there's a lot of strategies here. I don't want to give away all the secrets. Which of these streams do we think is going to be the easiest to handle?
Probably the feed.
Why the feed? Feed's going to be a liquid.
Okay, and it's not ideal.
Yep.
Well, the vapor, if you treat it as ideal, would probably be the easiest to handle.
Yeah, so the enthalpy of the vapor here is going to be relatively straightforward, right? We can do the enthalpy, so this can just be average of the individual components. Because it's an ideal mixture, so we're just doing a molar averaged value of the enthalpy. So whatever the enthalpy of pure vapor A and pure vapor B, do a molar average of those two. But here's one of the problems. You know, where do I even start, right? I don't have a table that I can just go in the back and look up, you know, heptane or toluene enthalpy values. So I have to choose a reference state. So what makes sense as a reference state?
The enthalpy of the pure components is 0.
Enthalpy of the pure components in which phase and at which temperature and at which pressure.
Liquid.
Okay, so we have our reference state. We're going to say liquid. What temperature, what pressure?
298 and 4.6.
298.15 Kelvin. Pressure-wise, well, we can say, technically we do have to assign a pressure, but for the most part, we're going to assume that the pressure changes to enthalpy are pretty insignificant. But technically speaking, yes, we should. So we could use this as our reference state. I maybe would tend to think, actually, that we would want to do this at 101.3 kilopascals, because that's where we have the mixing data. But again, we're going to neglect that contribution. Now, if this is an extremely high pressure temperature scenario, then we'd have to be a little bit more cautious. But for the most part, we can kind of gloss over a little bit the enthalpy changes associated with pressure. So here's our challenge. So when we think about these problems, we're going to have, I always build a spreadsheet to help me, even if it's not, you know, if I'm not on paper, I'll still build a table, I guess, table's a more universal term. So I'm not sure what the best way to format this one is. Oh, I forgot something very important. Very cute. Energy balance. The whole point of the problem, I forgot that part. So, we can fill in these values relatively easily. Relatively being the key word there, just for a non-ideal system flash calculation. So now the key question is, how do I go from my reference state to the enthalpy values for each of these different functions?
Well, for the feed and the liquid, the paper gave us the excess. So if we've said the liquid is 0, and the total for the mixture is going to be the enthalpy for that stream.
Correct. Let's go through it a little bit more carefully just to convince ourselves that that's what's actually going on. The delta H of mixing, so in the case of enthalpy and volume, that's exactly the same thing as the excess enthalpy or the excess volume. Entropy is the one that stands out. So anything that has entropy in it, the excess is not simply just the delta H of mixing, because you're always going to have entropy being generated when you mix two things together. So anytime we see a delta, this is the final minus the initial. Final in this case being the mixed state, the initial being the unmixed state. So in the case of choosing our reference state very cleverly, the unmixed state enthalpy is 0. So that way we can look up the heat of mixing and know that that is actually equal to our enthalpy value that we can actually fill into a table here based on how we've done the process. So let's say, for example, hypothetically, let's see, that paper also has the excess heat capacity, so you could use that. So for example, what I could have done is I could have said that the flash separator operated at 350 degrees Kelvin, but I only gave you the delta H of mixing at 298 and then the excess heat capacity. You could mix the two and then use the excess heat capacity to calculate what the new heat capacity of the mixture was. So there's lots of different ways that we can go about solving this particular problem. Okay, so that should help us fill in all of these values here, right? And what about the vapor stream?
You have to account for the enthalpy of vaporization.
All right, so let's take a look at the delta H of vaporization. This is the enthalpy of the vapor minus the enthalpy of the liquid. So again, if we've chosen our reference state cleverly, this goes away. But this is going to be at 298 Kelvin, which is not going to be the normal boiling point. The normal boiling point is going to be, I think, 98 for heptane and, no, 110 for one of them. I can't remember exactly. I think heptane's 98 and toluene's 110. So we'll have to find a way to estimate the heat of vaporization at this lower temperature, and that'll give us the information on the enthalpy. I cheated, I just looked it up. You can calculate it, or you can calculate it if you know the heat capacity of the liquid and the heat capacity of the vapor. But again, I just looked it up. I was being lazy. So I view this as all part of kind of review for the exam, because we've been focused a lot of time on vapor-liquid equilibrium. This one here reminds us where we started on multi-component mixtures, which is the heats of mixing excess properties. And then once we got to excess Gibbs, then we could really unlock vapor-liquid equilibrium because we had access to activity coefficient models and our understanding of what the activity coefficient was. You see kind of a lot of puzzled faces.
My question is, I mean, So when we have a liquid mixture, the heat of vaporization should be different than the pure components themselves.
Correct. But we are vaporizing the pure components. So the reference state is for toluene, enthalpy 0 when it's a liquid at 298. The reference state for heptane when it's a liquid at 298 is 0. So we never have to unmix. Now if I were to give you the reference state, what if I said the reference state is the mixed system at 298? Then you would have to unmix, where you'd use the negative of the excess, then that would be the enthalpy of the pure components, then you could vaporize them. But in this case here, we are only mixing in order to get the liquid enthalpies. So in this case, actually, we don't care about this. We care about this value and this value.
Right.
You're not looking at the enthalpy of the individual species. You're looking at the enthalpy of the combined system.
So we don't really need the excess enthalpy for the vapor, or
No.
I guess there isn't any,
No.
because it's ideal.
Now you still could have some non-ideal. I don't know.
Okay. There's my
Do you ever really have heats being released when you mix two? I think you technically can, but this is low pressure vapor liquid equilibrium, so ideal gas should be very good analogy. So in question 1, I'm not expecting unique values of the tau and the alpha and things like that. I'm just looking for a good match of the excess data. That's the main task. And then question 3 is really just reinforcing that the full solving solution approach to reacting systems is solidified, and also looking at changes in temperature or changes in the reactor environment. So you should be prepared for all similar types of questions. So I'll do a quick recap. So stop me along the way if you have any questions. Otherwise, I'll just kind of run through the default material that I have prepared. So the main emphasis is going to be mixtures, specifically a lot of emphasis on multi-phase mixtures, but let's not forget that we still have single-phase mixtures. How this all began was partial molar properties. So theta is used to represent any molar property. Subscript I lets us know that it's for that species. Overbar indicating that this is the property within a mixture. We've defined this. As how much does the total system property change? Right, this is again a function of temperature, pressure. Then the X underbar is the quick-hand notation we use for saying composition as well. How does the total molar property change with respect to adding or subtracting a little bit of species I, but doing this mixture at a constant temperature, pressure, and holding all the other things constant? Now, one thing to really keep in mind, same thing with activity coefficients as well. Due to the Gibbs-Duhem equation, we don't know who's responsible for excess properties. It's not clear if it's component A adding it into B that's sort of acting up and causing there to be excess properties, or is it B, who's responding to A into the mixture. So really what this is just a way to keep track and tabulate what's going on, but no one's really responsible for the energy being released or the volume being changed or excess entropy of mixing, things like that. Right, this is just a way for us to categorize and organize the information, specifically with respect to activity coefficients. So this is the partial molar property, but we also defined and spent a lot of time dealing with excess properties. So in the case of excess, This is the change of mixture properties versus how the mixture property changes ideally. Oh, partial Molar area up there. And the connection, we can write a well. So if we do know all the partial molar properties, we can then do a weighted average to give us the mixture property. Oh, sorry, not delta mixing. It's just the theta property. So we can manipulate this in many different ways. Now, this is interesting for volume changes, enthalpy changes, but what we were most interested in is looking at the excess Gibbs. The reason why we have to define excess properties is because ideal mixing for entropy is not 0. So there's something to consider there. So when it comes down to actually keeping track of unique thermodynamic data for all sorts of mixtures, we don't want to have to include the complex functionality that's associated with the entropy of mixing, right? This x times natural log of x type business. So instead, we're only going to tabulate what is the additional interesting information. So there's a mountain of ways that we can write these systems, and you got a handout a while back. This is the partial fugacity coefficient, which we can substitute in as the partial fugacity effectively divided by the fugacity that it would be in an ideal mixture. Pure component fugacity times by the mole fraction. That's normally the fugacity, partial fugacity for an ideal mixture. This is the actual fugacity, partial fugacity in the real mixture. And that's related to the excess Gibbs of that particular species. From here, we also define the activity coefficient. Right, because the activity coefficient is effectively just directly related to the excess Gibbs. So the notion here with the activity coefficient is that we're just going to lump all of the non-ideality associated with phase equilibrium and just slam it into the activity coefficient, which allows us to unpack it relatively straightforward, because if we know the activity coefficient, then we basically have access to understanding how the phase equilibrium behaves. So it's a little bit cheating, right? We're not actually, for most scenarios, we're not directly calculating the activity coefficient. Now, there are predictive activity coefficient models that can be used, but for the most part, we're just lumping everything that we don't know into one term. So for low pressure vapor liquid equilibrium, which is the lion's share of the types of calculations that you're going to see in the laboratory or in a sort of standard chemical process, activity coefficient is the key. So if you know the activity coefficient as a function of temperature and as a function of composition, you can basically use that information to solve all the phase equilibrium that you would be interested in. Liquid, liquid, vapor, liquid, and so on. And then the final, the equilibrium criteria, is that the partial fugacities for every species is constant across all phases. So just like the first exam, when you reach a new question, try and digest it and think, what are the concepts that are being asked? Is this a phase equilibrium question? Here's my starting point. What are the assumptions? Ideal vapor, non-ideal vapor, ideal liquid, non-ideal liquid. And from there, you can effectively build out a matrix of what is necessary. So, vapor-liquid equilibrium. Starting point is that the partial fugacity of species I in the vapor phase is equal to the fugacity of species I in the liquid phase. And it's just a matter of how do we approximate each of these different terms. And then solve the system. So the thermodynamics is here by starting off. Then the next step is once we know how to approximate this, it's all just math. Right? So for the most part, the thermodynamics ends when you've stated all your assumptions and you've simplified the expression. So we can do a couple of steps. This is the Lewis-Randall rule. This is okay for ideal mixing of the vapor phase. Right? This is a non-ideal pure component with ideal mixing. Also called the Lewis-Randall rule, but note this is ideal volume of mixing or ideal mixing for the vapor phase. The fugacity of a pure ideal gas is just going to be equal to the system pressure. That's another approximation that we can introduce. For the liquid phase, this one's no assumption so far. All we're basically doing is relying on the definition of the activity coefficient. So again, if you substitute this in, it's really cheating, right? We define the activity coefficient as the partial fugacity divided by the fugacity of an ideal mixture. So if you substitute it in, you just get that the partial fugacity of the liquid is equal to the partial fugacity of the liquid, right? So again, it's just a cheat. All we're doing is finding a way to categorize and organize this information. All right, so let's offload this from me. What's an approximation we can do? State a physical approximation. How do we assume this model is going to behave? And then let's write out different ways that we can approximate the fugacity of a liquid, partial fugacity of a liquid. Give me an assumption. Ideal mixing? Okay, so in ideal mixing, what happens there?
No gamma.
Activity coefficient.
Okay, what's another approximation we can do? We don't have to build on this one. Start from this point here. So we're going to do each of the individual approximations, and then we can see how we want to slap them together. What's an approximation we can do here? How do we get access to this information?
Low pressure system.
Low pressure. Okay, how low?
The fugacity of the liquid would be equal to the fugacity of the vapor at the saturation pressure.
Good, I like that one. So that's so this is low pressure, and that's actually the more appropriate. So in this case, X gamma, and then this is the so what we've done is we've neglected the Poynting correction. Okay. There's, I think, one more left that we can pull out.
It's like an ideal fluid. Keeps the vapor pressure. Instead of fugacity.
So we want to write this one here, right? Because this is what we've been familiar with. right? What is the assumption, the physical assumption that gets us to this approximation here?
The vapor phase is ideal.
Ideal vapor phase. So we're at our ideal gas. Vapor. I want to highlight one additional way here. When you look at the practice exam, you'll sort of see why. If we do have non-ideality in the vapor phase, where we can look up a partial fugacity coefficient, or we can also just look up a fugacity coefficient for the pure fluid. There's a lot of ways to look at this, right? So if I do throw something at you that's a little bit stranger, I won't kind of, I'll kind of give you a nudge in the right direction about how you should be thinking about the approximations. But when you look at the practice exam, you'll understand why I included that one. Okay, so I've got some other notes here about dew curves and bubble curves. I think everyone should be pretty confident with those. Let's see. Yeah, so TXY, PXY diagrams. Do you have a question? Oh. So does anyone have any questions on TXY diagrams, PXY diagrams, dew curves, bubble curves, flash calculations? We've really hit those over the head. So instead, just remember XY diagrams and azeotropes and flash separations. Those are all topics that we discussed. But instead, I'd like to go over a little bit on, spend more time on liquid-liquid equilibrium as opposed to vapor-liquid, which we had a lot of experience on. Okay, liquid-liquid equilibrium. This is an equilibrium problem. So what is our starting point? Right, we call them arbitrarily phase 1 and phase 2 because we don't necessarily have a good name. One of them we typically like to call as component 1 rich or A rich. The other one we like to call component 2 rich or B rich, meaning that it's the one that's the most concentrated. So in liquid-liquid equilibrium, if we have an ideal liquid mixture, is anything happening?
No, you wouldn't have phase separation.
Everything is miscible in an ideal mixture because you have a contribution to ideal mixing from the entropy of mixing, meaning that when you mix two fluids together, you automatically gain a tremendous amount of entropy. So all phase separation occurs when the two fluids don't like each other so much that they can actually overcome the entropy gain when you mix the two fluids together. So if you don't have activity coefficients, you will never get phase separation for a liquid-liquid system. So that gives us sort of a bookmark of how we can approximate liquid-liquid equilibrium. So if we look at an activity coefficient approach, this is all phase 1, phase 1, phase 2, phase 2. Right, so we're not doing anything differently than just rewriting how we approximate the fugacity coefficient of partial fugacity of a liquid. I've made 0 assumptions. All I have done so far here is I have invoked the definition of the activity coefficient. That's it. And it just so happens that this is what they call a simple mixture, even though it's much more complicated to calculate, that the pure species fugacity cancels out. Now, I don't have to assume that that's the vapor pressure. I don't have to assume it's an ideal gas phase. I don't have to make any assumptions. All I'm using is the definition of the activity coefficient. So when it comes down to it, the governing equation for liquid equilibrium is just basically unpacking the definition of the activity coefficient. So whichever method you'd like to use for the activity coefficient, all we're doing here is unpacking that information as a function of temperature, as a function of composition. So that's why vapor-liquid equilibrium is a very useful technique, because that's how we used it to calculate the activity coefficient. Now, if you had a liquid-liquid system where you didn't have vapor-liquid equilibrium, you would basically have to measure the liquid-liquid phase separation and then tune your activity coefficient model so that it accurately predicted the solubility of A into B and B into A. Graphically, so mathematically, this is it, right? Just substitute it in. For a two-component system, you have two equations, two unknowns. For a three-component system, you have to have an activity coefficient model that can take x1, x2, and x3. For a four-component, x1, x2, x3, x4, so the model can get significantly more complicated. So graphically, though, I think it's a little bit nicer to think about liquid-liquid equilibrium. It's kind of more intuitive to understand when we look at it graphically. So let's say this is Gibbs 2, this is Gibbs of 1. So if I just were to average these two together, we would get a dashed line. That's effectively how much Gibbs is individually poured into this pot. I have an additional contribution from the entropy of mixing. Right, so I gain entropy when I mix, so that means that no matter what happens, right, this is the Gibbs that I'm throwing into the pot. Every single point on the curve is lower than the Gibbs that I have contributed to the fluid. Now, if I start to have non-ideal or excess Gibbs of mixing, then we can start to pull this up. And eventually, we'll get an inflection point if they phase separate. When they phase separate, the equilibrium is at the tangent of the lines that connect those two at the bottom. Now, it's not perfectly obvious, but the tangent is actually the lowest drop in the Gibbs when you have this kind of line skewing things a little bit. But this will be our two compositions. Now, we know that there's phase separation occurring because we've created an unstable fluid. We know an unstable fluid based on the curvature, in this case where the curvature of the Gibbs free energy is less than 0. And this is all based on the stability criteria of entropy. Entropy, as we recall, has to always be convex with respect to anything. Temperature, pressure, composition, phase, no matter what. Right? The entropy is always increasing, but the rate by which it increases always starts to level off. If this is not the case, then you will have an unstable universe and everything will catastrophically fall apart. So in the case of entropy, with respect to any variable, always has to be less than 0. Now, if the Gibbs has the same, that means it's unstable. So Gibbs is stable when it's convex. It takes me a second to remember those two. So in general, two fluids don't like each other. In the case of toluene and heptane, they don't much like each other. They'd much rather be by themselves. So if you grab any two off-the-shelf chemicals, odds are they don't like each other as much as they like with being with themselves. Now, we have a lot of experience with systems that have, let's say, negative enthalpies of mixing, meaning they release heat like sulfuric acid in water or salt in water, or systems that kind of dissolve. To us, we work with a lot of systems that do dissolve, because if they don't, then they're not particularly interesting or useful systems. So the set of materials that we work with is biased towards things that do dissolve into one another. But in general, any two off-the-shelf chemicals don't want to mix. Like if you go to the Fisher catalog and randomly grab two things, they won't want to mix. Or they will, but they'll probably be endothermic mixing processes. And that's what you see with the heptane toluene mixture. That is an endothermic mixing process as well. With hydrocarbons, traditionally you have positive excess entropy and positive excess enthalpy. Meaning that the enthalpy says the two don't want to mix. The entropy says the two mix, but they gain actually more entropy than you would have expected normally. So in many ways, hydrocarbon mixtures are actually dominated by the entropy of mixing as opposed to the enthalpy of mixing. Yeah, they're endothermic, but they really don't hate each other that much, so it's not that big of a deal. Okay, questions on liquid-liquid before we do a really last quick recap on the reaction equilibrium. So for any general chemical reaction, so chemical reaction equilibrium, for any arbitrary reaction, these are the stoichiometric coefficients. We can write the number of moles for any particular species as the initial number of moles plus the stoichiometric coefficient times by the extent of reaction. So in the case here, these are negative numbers. These are positive numbers. And this convention just allows us to write reactions universally, so we don't care if we write this forwards or backwards. So in kind of research or industrial level reaction equilibrium models, you may have hundreds or thousands of molecules or reactions occurring. You don't necessarily know which one's going forward, which one's going backwards. It doesn't matter. The stoichiometric coefficient can be positive or negative. Sorry, the extent of reaction can be positive or negative, and the stoichiometric coefficient can either be positive or negative. So if you adhere to this convention, it doesn't matter what the system does, it matters how you write it down. On your paper, if you write the reaction this way, A and B are negative, C and D are positive. So that when your code spits out what the extent of reaction is, you can reinterpret it, right? Because if you switch it up and you flip it around, all it does is changes the sign of the extent of reaction. Right, so it's the convention that just stick to it so you can unpack your own calculations. So equilibrium is established when this criteria is satisfied. When the summation of the stoichiometric coefficients times by the partial Gibbs free energy is satisfied, then you are at equilibrium. So we introduce a little bit different convention here. Now, if you had an equation of state, we could directly use that equation of state to calculate the partial Gibbs using a Fugacity coefficient calculation approach. Conventionally, though, we try and do something a bit different. We define the activity. Again, this is clever arithmetic. We're going to define the activity as the partial fugacity divided by the partial fugacity at some standard state. Not reference state, standard state. Reference states you can control, I can control. Standard state is when everyone has sat down at the table and said, okay, if we're going to measure reactions and tabulate it, let's all do it at the standard state. So in that case, the standard state is at mole fraction is equal to 1, which is kind of cheating, so basically we're saying it's a pure fluid. Temperature, 298 Kelvin, or 25 degrees C, and pressure of 1 bar. So when you look up reaction information, they will almost always be tabulated at this condition. If not, it should be explicitly clear under what conditions they were tabulated. So with this clever arithmetic, what it allows us to do is to separate the temperature and pressure effects of a reaction. So we can write that the change in the Gibbs of reaction is the summation of all of the formation reactions. So effectively the way that we can view this is if we take a compound, we explode it into its atomic contributors, rearrange those, and then form the products. That's effectively what's going on here. Since this is thermodynamics, we can choose the path, right? We don't actually have to follow the real pathway that the reaction changes. We don't have to look at the intermediate steps, the transition states. We can just explode everything to atoms, rearrange them, and then reform the molecule of choice. So this here is going to be a function of the temperature. Let's see, yeah. We could also do this at the standard state. Delta reaction Gibbs at the standard state, in which case this would not be a function of temperature. That would be what the delta G of reaction was at the 25 degrees C, pressure 1 bar. We can write an equilibrium constant as the scaled form of the Gibbs free energy of reaction. So the equilibrium constant here is going to be a function of temperature because the Gibbs of the reaction is going to be a function of temperature. Right? Effectively, this means how does the Gibbs free energy of the reagents change with respect to the Gibbs free energy of the products as you change the temperature. But we can also write the equilibrium constant as the product sum of the activities raised to the stoichiometric coefficient power. Now, for the majority of what we have done, we have approximated this as an ideal mixture. Let me do this here. The activity for ideal gas don't forget this pressure equals 1 bar. Activity is a unitless quantity, but that's only because it's been arbitrarily normalized by the standard state fugacity, which is the pressure of a pure ideal gas component, which is just the pressure, so whatever pressure we've chosen for that standard state, 1 bar, which is relatively close to normal atmospheric conditions. That's how we write this here. But if we had a non-ideal system, right, we could of course include a fugacity coefficient into that mixture as well. Or if you had an equation of state, you can directly calculate the activity through directly calculating the partial Gibbs or the fugacity coefficient there. So typically what we've done in the past is that if you have an unequal number of products and reactions, the pressure of the system and the mole fraction can be written as the number of moles of species I divided by the total number of moles in the system. So if you wanted to write this out on one big sheet of paper for a complex system of reactions, it would be heinous. A lot of different things to write down, but instead, if you can organize this some way in a table and break down the calculations into smaller steps, it makes it relatively straightforward to solve in Excel or MATLAB or some other software package. So we haven't really done good justice to reaction equilibrium, but for the most part, it's exactly the same as phase equilibrium, right? It's a slightly different convention. So any non-ideality that you want to consider in a reaction equilibrium scenario is just right here. How do you approximate the fugacity coefficient of a non-ideal vapor? How do you approximate the fugacity coefficient of a liquid? So in the case of a liquid-liquid reaction mixture, instead of having y times p, it would just be approximating the partial fugacity of a liquid, which means all down to the activity coefficients. So if I gave you a liquid-liquid system, right, let's say A and B are partially miscible, and they have an activity coefficient, that's going to impact how the reaction occurs. Right? So this is the novel contribution to reaction equilibrium. But the part where we approximate the fugacity, that's exactly the same as phase equilibrium. Right? Some might be more popular than other approaches because of the systems that are conventionally studied, but at the end of the day, if you want to model a non-ideality, you just have to choose a model for the modeling the fugacity. Again, like I said, we're just unpacking and we're teaching the system of how it goes. So this is the novelty associated with reaction equilibrium, but everything else we can just borrow from all the other topics we've discussed. Okay, any last minute questions? No stat mech on the exam. We've got plenty to talk about in the absence of that. If not, so Chinmay will have office hours right now. He has access to the numerical solution, so you can double check your work or find out all the errors that I've made. I'll have office hours tomorrow from 12 to 2 for any exam questions, and apart from that, see you all on Friday.